Good afternoon, everyone. My name is Nagendra Singh Tomar. I am the product manager for X-ray and CM from BPL Medical Technologies. So today is a very special day because today on 8th of November 1995, William Conrad Ranjan discovered some new rays which were unknown that time, but today we know that as an X-ray. So, okay. So I'll just, in the next 15 minutes, we will have a discussion on a few topics like, basics of X-ray generator and X-ray tube, and what is KVMA, kilowatt rating, that is the C movement, and the general specification of SIAM while we are buying a new SIAM, what all the specs of SIAMs available in market. Okay. So as you are aware that you all have been using the C-arm. So on the right side, you can say this is, we call it C-arm or buggy, and left side it is, workstation, or we call it trolley. So you can see here it is a control panel from where you can control all the features of C-arm. In most of the C-arm, you would find the control panel is given onto the buggy. In some of the C-arms, like high-end C-arm, you will find that it is onto the top of the arm, so that you can swivel it to the both side, and it is more user friendly. Obviously, nowadays flat panel C-arms are available, but most of the C-arms still available with image intensifier and with camera, because still the cost of flat panel is very high. But we hope that in future that will come down. And why we call it a C-arm, basically, you can see that there's a C-shaped semicircular arm, and on top of that, you will have, image intensifier camera, and bottom, you will have X-ray tube head, or we call it monoblock. And the left side, you will find two monitors. One is for live fluoroscopy, and other is for reference image. You will have a image processing unit. And in some C-arm, you will have a display on control panel as well. So total, you will get a 3 display in some C-arms. This display on control panel is basically for the operator. So operator no need to view the image, at the trolley side. He can always see the image onto the control panel and align the C-arm accordingly. Okay, so this is the flow chart, and this flow chart was also shared by Dr. Sonamane. But again, just I'll repeat it. On the bottom side, you will see the X-ray generator and tube, and then you will have a collimator. Obviously, there will be a fixed collimation which will limit the beam up to the size of image intensifier, so that beam should not go out of II. Or you can have as an external collimator also, like iris or parallel shutter. There will be a filtration just to keep the dose as per the under the regulatory limit, which is decided by the ARB. Then you will have a table, and a patient is there on that. After beam is passed through the patient, obviously there will be some scattering. So that scattered we remove by using the grid. And grid could be of different ratio, like some uses 8:1, some other uses 10:1. Obviously higher is better. Then you have image intensifier, which convert X-ray into electronic signal, into light signal basically. And then light is again captured by the camera. Then further signal sent to the image processing unit, and then you will get the display of images onto the monitor. And the right side, you can see all these is controlled by the control console, which is there, onto the C-arm buggy side. Okay. So in X-ray generator, there are always two parts. One is inverter, which is always there at buggy side. In beginning, we were talking about some fan and all, but yes, inverter side fan is mandatory, and it is available in almost all the C-arm, because we have to cool the inverter as well, because there are a lot of circuitries in that. Second is the monoblock. Monoblock is the tube head. We call it tube head or monoblock. So what is the function of inverter? It is very simple. Basically, you would have seen at our homes that, if light goes, then we have, inverter at our home. So what does it do? You have 230 volt, 50 hertz, input power supply. You convert that into first DC. DC is stored into the battery, and again, then DC same convert to the AC signal and give back to the appliances. But here is a slight difference is there, that 50 hertz we convert to high frequency. It could be 40 kilohertz, it could be 100 kilohertz, it could be 200 kilohertz also. And that 230 volt, we convert that minimum to 40,000 volt. because in Siam you will see that minimum range is 40 kV and higher range could be 110, 120, or even 125 also, high kilowatt Siam. So that difference is there. So first we convert AC to DC, then we increase the frequency, that again is DC is converted to high voltage AC, and finally the what we gives to tube is, that is basically a DC voltage, high voltage, and on high frequency. Now this is the monoblock, or we call it tube head. So on top of the part, you can see this is the tube insert, which is inside the glass, envelope, and there is no air. A vacuum has to be there. And bottom side, you will see this is the high voltage section, which convert that low volt to the high volt. And on top of this, this is X-ray window. From there, you will find that X-ray will come out. It has got obviously a fixed collimation ring, and this tube is covered by the lead lining so that leakage should be as minimum as possible. On this side, you will have a heat sink so that heat gets dissipated by the oil. Right side, this is a bellow inside that, so that temperatures, when the temperature increases, so oil expand, and that time bellow works in that time to adjust, so that no bubble should come even when tube gets heat up. And bottom side, this is a high voltage section. So this is just a monoblock, the major parts of the monoblock inside. And obviously this is the main part, because this is the heart of Siam. Okay, X-ray tube, as we all know that there are two main parts. One is anode and cathode. So anode is the left side and cathode is the right side. From right side, electrons emitted strike to the anode. Okay, and then finally you get the X-ray beam. Okay, so there are two kind of anodes. One is stationary and rotating. In the high voltage generator, we always have a rotating anode. Or you can simplify this up to 100 mA you can easily go with the stationary anode. But if you want to go beyond 100 mA in radiographic output, so that in case that you do require a rotating anode Siam. And right side you can see rotating Siam is little bit bigger as compared to stationary anode Siam. So stationary anode Siam is compact in size. So the monoblock, which has got rotating anode Siam, obviously those are more powerful, but those are little heavier also, in the size, in the weight also. Okay, and little bigger into the size. Obviously, second is the cathode size. So cathode means that from where the electron starts and is strike to the anode. And on this picture you can see there are two filament. So two filament means there's a large filament and the small filament. So large filament is for largest focal spot, and smaller filament is for smaller focal spot. So in our Siam, we have two focal spot. One is smaller and other is for a large focal spot. So smaller is basically for fluoroscopy, and large is basically for radiography. Okay, so this is line focus principle. Very important features, very important topic. When we talk about X-ray, we always talk about the focal spot, especially in Siam. And you will find that in most of the Siam, focal spot are same. All the manufacturers provide almost same focal spot for that is defined for stationary anode, which is 0.6, and large could be 1 or 1.5, depends on to the manufacturer. And in rotating anode, you will have 0.3 and 0.6 focal spot. So 0.3 is for fluoroscopy and 0.6 is for radiography. So you can see the effect here, that if your target angle is fixed, that is 15 degree, and you have incident electron beam of this size. So left side is bigger and right side is smaller. So the target area is called focal spot. So you will see that central ray, we call it effective focal spot, is large if you have large actual focal spot. But if your focal spot is smaller, then your central ray again would be smaller. Means your effective focal spot will be smaller. So we always talk about this, in specs, incident electron beam. We don't talk about the smaller focal effective, because that is dependent onto the tube target angle. Now in this same size electron beam, so left and right side both are same. It means your actual focal spot is same, but your target angle is different. So right side you have a 12 degree target angle, left side you have a 14 degree target angle. But again, if your target angle is small, then your smaller effective focal spot would be as compared to large angle. So whenever you buy, any CM, just check whether obviously focal spot will remain same. What is the effective focal spot, and that you can determine by the target angle. Now, penumbra effect. I'm sure that you all are aware about the penumbra effect. Is like, if your source, let's say these points are light source. So if your source is very small, and this round icon is, let's say, object, and this is screen, so you will get a very sharp image. If you will make the source bigger, that you will have a kind of double edges, and it is further bigger, then you will have again prominent double edges. It means that if your source is small, your image will be sharper, and the object should be as close as to the image receiving end, image intensifier, or X-ray film size, so that you will have a less effect of penumbra. Okay, so smaller focal spot is better, but yes, if smaller effective focal spot is better, and then you just just check how much the target angle of the tube. So in normally in stress rotating anode, target angle is a little smaller as compared to stressing anode. Next is the X-ray tube housing. As we are talking about the obviously radiation safety, so the housing should have proper shielding due to lead or any other material also can be used, which has got high atomic number like antimony, bismuth, antimony, and all. It is used basically so that from beam there should be a minimum leakage radiation, as well as your tabletop dose, the X-rays which are passing through the patient, and you will get the image quality, that also should be in limit. Okay, so these are the two parameters from radiation safety side. Now come to the heat. Obviously, heat is major in portion in X-ray production, and you can see this is the target area. We call it radiation. Electron all will fire to this target area, so that from opening you will get the X-ray. But in this process, 99% is heat generated, whereas 1% is only X-ray. And this heat is again transferred through the conduction method to the anode stem, and it will go to the oil. And on periphery of that, you will have a cooling fins, like there could be passive cooling, active cooling, depends on to the X-ray tube. And you can also have fan, which we call it force cooling, just to exhaust that hot air which is there inside that monoblock. But yes, we have to take care. If we are having fan, there should not be any ingress of fluid inside the monoblock, because that will create hygienic disadvantages. But I've seen in most of the CM, especially for ortho and all, we don't use any convection method or any fan and all. Okay, so let's discuss about the actually whenever we talk about X-ray machine, we always talk about MA. We don't talk about kilowatt. But actually, what is MA? MA is the amount of X-ray, kV is the penetration power. So when we talk about the power, P is equal to voltage multiplied by the current. So we always talk about the kilowatt, because kilowatt will only tell about the maximum output of the X-ray or CM. So what is the effect of kV? As we all know that kV is the penetration ability of the X-ray photon, and it produces contrast into the image. So like on X-ray film, once kV are higher, you will get a bit dark image. But obviously in CM it is other way around. In CM, higher the kV, brighter the image. But obviously it will you can lose away the contrast from that. So kV has to be optimum depending onto the thickness of the object. Second is the MA. MA is the basically amount of X-rays. MA is the amount of X-rays which creates a density into the images. So obviously your selection of kV and MA has to be proper to get an appropriate image quality. Okay, let's talk about again kilowatt. Why I have just talking about this. See, whenever we talk about the CM output, It could be 2.5 kilowatt, 3.5 kilowatt, 5 kilowatt, 6 kilowatt, or higher. This is basically, radiographic mode output. And please, as you all know, that we don't use radiography nowadays into SIAM, because our memories are digital and we have got multiple operating modes into fluoroscopy. But you just see the example, if you are going for the 2.5 kilowatt, it means that 100 kV, it will generate 25 mA for 100 milliseconds. So that's, define the maximum output. Like in old days, we always talk about the MA, 100 MA X-ray, 300 MA X-ray, 500 MA X-rays. So that was right, but that was at 100 kV. So 100 MA at 100 kV, if you are getting perfect. If you are getting 300 MA at 100 kV, perfect. But in high frequency, when you talk about the X-ray output, MA cannot tell you the exact maximum output of the generator. So same way, 3.5 kilowatt will give you the 35 MA at 100 kV for 100 milliseconds. That's become 3.5 kilowatt. Just see the second part. Suppose you have somebody says I have 100 MA X-rays. So 100 MA, if you are getting at 100 kV, that becomes 10 kilowatt for 100 millisecond. 100 MA, if you are getting at 100 kV for 100 millisecond minimum, that becomes 10 kilowatt. But if you are getting 100 MA at only 40 kV, that becomes 4 kilowatt. So there is a major difference here. Both the units are 100 MA, but kilowatts are different. Obviously, 10 is better than 4 kilowatt. So we should always talk about the kilowatt output. Let's come to the fluoroscopy mode. That is more, obviously that makes more sense in SIAM. Like, we uses sometimes 3 MA at peak power. Let's say 110 kV is the maximum, kV limit of SIAM. Sometimes we uses 5 MA, 8 MA, or 10 MA. Now left side, you just see the wattage. So 110 kV 3 MA becomes 330 watt. 110 kV at 5 MA becomes 550 watt. 110 kV at 8 MA becomes 880 watt. And 110 kV at 10 MA becomes 1.1 kilowatt.
Right.
So it means...
So please come down to clinical application so that we can finish up the program in time.
Sure. Yeah. Let's come to the manual factor selection. Basically, although we always select that we should use auto mode. Because auto mode is because if your technician is not well versed with the SIAM, that manual selection of manual factors would be a little difficult. But these are just an indicative kV MA parameters, because this will change based on to the construction of your SIAM. If you have a half K by half K, the MA could be different. So if you have 1K by 1K imaging chain, the MA could be different. Even in flat panel, MA could be different. Okay, but this is just an indicative, KV MA factors. Like if you have adult normal or adult large, and you perform the lumbar spine or hip, so your KV would be around 65 to 75 KV in normal case, 75 to 80 KV in large patient, obese patient, and your MA would again vary from 3 to 4 or 4.5 up to 4.5 MA. In adult normal and large femur case, obviously you require near about 63 to 65. And you goes up to 2 to 2.5 MA. That is sufficient. You can get the...
Yeah. Again, now come to your conclusion slide, please. Thank you.
Yeah. Okay.
Yeah.
So my conclusion slide is basically major specification of the SIAM. So you will get a 2.2, 2.5, 3.5. So don't bother about the kilowatt output, because that is a radiographic output. Any generator more than 1.5 kilowatt is sufficient. You have to decide, whether you want to go with the Stacy anode or rotating anode tube, but your, cooling rate should be better, so that tube should not get heat up. You should also have real-time temperature indicator onto the console, so you can easily check, how much tube is heat up. You no need to go to the, tube is got heat up and then you start reacting to that. So you can plan your surgery accordingly if you have, real-time temperature indicator. Everybody has got 9-inch image intensifier, but there are 2 intensifiers available, that is 48 and 52 LP per centimeter. 52 is always better. Camera, you have nowadays CCD and CMOS. Obviously, CMOS, CCDs are getting obsolete from the market. So CMOS will continue for some other time. And you have half K by half K basic CM and 1K by 1K. So 1K by 1K nowadays are getting cost effective. You will get even less than 15 lakhs rupees. So we'd prefer if you can go for 1K by 1K imaging chain, that is good. In operating modes, you have multiple operating modes: continuous fluoro, pulse fluoro, high contrast mode, DR mode. Make sure that your CM should have auto dose mode. You no need to select anything manually. Just give the exposure and you get the automatically image onto the display. Now, major why we sometimes we don't use auto mode is because the poor response of auto mode. It is something, some CM, it is very slow. So make sure the CM which you buy should have 40 greater than or equal to 40 kb per second speed. So it should have fast response. There are like two kind of memory available embedded, which is of 100 frames, or PC based also. So in PC based, you get the different protocol. You can create protocol as per the anatomy, like for lumbar, different protocol. For cervical, you can create the different protocols. So which are very useful, and we should go with the real-time brightness contrast also. Sometimes, we just struggle with the, minimize or maximize KV and MA. So if our system have, software control, with the help of software, we can change the brightness and contrast of the images. So obviously that is, helpful. And collimation is very important, and we should have a virtual collimation. Why we don't use collimation in India? Basically, because in very high-end CM you'll get the virtual collimation, but the cost is very high. So those are the normal collimator. So once you have to align the collimator blade onto the images, sometimes response is not good. Sometimes, most of the time you have to expose to just align the collimator blade. So just you will forget, okay, leave it. Let's not do it. If you have a virtual collimation, you can align collimator blade onto the last image hold. And this feature is now also available in entry-level CM.
Okay.
You can have a navigation compatibility for future upgrades and dose display.
Yeah.